Before we say the definition of the integral, let's remember how it worked for a derivative. We defined what the derivative was by saying if you have a function and it's defined near a, you want to find the slope at a, then the derivative is the number that is approximated by the difference quotient, where the approximation gets more and more accurate as that b value gets closer and closer to a. There were kind of two parts of the definition. We had to say how you approximate the derivative. You approximate it by computing its difference quotient. And then we also have to say, how do you make that approximation better? The approximation needs to be able to get better and better. And for the derivative, the way you do it is you change that value b to get closer and closer to a. And as long as b is close enough to a, then your derivative will be a good enough or the difference quotient will be very close to the derivative. You can get more digits, so on and so on. How does this work for an integral? If f of x is a function, and it's defined on an interval, an interval here from a to b. That last example, we were talking about how far did the fly move on the interval from 0 to 3. We needed to know what is the function doing on the entire interval from here to here. So if f of x is a function defined on an interval a to b, the integral of the function from a to b, so we need to know what is the function and what range are we working out the function over. These are the two parts written. The integral from a to b of f of x dx. We'll zoom in on this in a second and say how we write down this integral expression. The integral is the quantity, is the number approximated by computing what's called a Riemann sum. Of the function over the interval. Now I need to say what a Riemann sum was. For derivatives, it was just the difference quotient. We could write down a formula. It was pretty easy. For a Riemann sum, you need to add up a bunch of numbers. We need to explain where do these numbers come from in our definition. Here's how we come up with that. Where did we come from the Riemann sum? A Riemann sum is computed by first we need to divide the interval a to b into smaller subintervals. Subintervals. Usually we say n subintervals. We use n to be the number of subintervals we cut it into. They don't have to be the same length. We can cut them into unequal pieces, but that's kind of a weird thing to do. Most commonly, if we cut it into 10 pieces, then it'll be 10 pieces of the same length, each having length. The name we give for the length of the pieces is delta x. The letter might not be x. The letter is whatever the input letter for our function is. For this definition, we'll say that that thing is x. So take that interval, cut it into pieces. For each piece, we need to choose a representative x value. How do we choose a value? Well, it kind of doesn't matter, although the instructions will usually give you some information on how to choose an x value. What I mean by this is, for the interval from 0.5 to 0.75, this stupid stylus. Hang on. So for the interval from 0.5 to 0.75, when we were looking for the minimum speed, we plugged in 0.5. When we were looking for the maximum speed, we plugged in 0.75. One of them gave us this as our Riemann sum, the other one gave us that as our Riemann sum. There's different choices to make that will give you different Riemann sums, but all of those Riemann sums should be approximations of the interval. So for each interval, we choose a representative x value. Some definitions will call this the x star value or something. What do we do with those x values? We plug those x values into the function we're integrating. Multiply those outputs each by the length of the interval it represented, and then add up those products. Let's go back and make sure we understand how this definition applies to the examples we just did. We cut the interval from 0 to 3 into 12 pieces. For each piece, we picked a number that we're going to plug into the function. In this case, we plugged in the left-hand number because we wanted an underestimate. We'll talk more about that in a second. We plugged in those numbers. We multiplied those by the length of the interval. In this case, every interval had the same length. I think in every case we ever do, they'll always all be the same length, and that keeps things nice and easy. There's reasons to do them different lengths, but we're not really going to talk about those. And then we took those products and added them up. It's a Riemann sum. A sum is the word for, the result of adding up a bunch of numbers. These are the things we're adding that give us this sum. And that approximates the integral. So this is how you compute a Riemann sum. The approximation of the integral by the Riemann sum, gets more precise as the length of the subintervals goes to 0. The subintervals don't have to be the same length, but as long as the biggest of your subintervals is very small, then this Riemann sum will be a good approximation of the integral. We say that a Riemann sum is a left-hand sum if the representative point you choose is the left endpoint. We do a right-hand sum by taking the right endpoint. We can talk about midpoint sum by taking the midpoint of each little subinterval. Like, this is the big question we have, is to compute a Riemann sum, you cut it into pieces, and for each piece you need to choose what's the point that's going to be the representative of this interval. How do we make that choice? Well, the Riemann sum will usually tell you some kind of instructions, or the problem that I give you will give you some instructions on that.